Now I'm going to do the question number 4 from the 2017 midterm exam. And in that question, we are given 4 waveforms, S1 through S4 in the time domain. And we're asked to find the basis vectors for signal space and to find the vector representation of each one of these signals in that signal space basis that we found. So there's 2 ways that we can do this. One is to use the Gram-Schmidt process, which is kind of like a recipe. It takes you through all the steps, how to get a basis vector. And the other one is what I'll call inspiration, or what I could call also inspection. Just by sort of looking at it, I get a good idea. So in this case, things are pretty simple, and I think you can get a little inspiration for what would make a good basis vector. And then on the second part, I'll start you off on the Gram-Schmidt process, and in the solution set for this exam, there's some very detailed development of the Gram-Schmidt process. But let's suppose you're a little calm on that exam day, and that you have a little time to think and breathe, and you look at this and you say, well, let me look. These are all square waveforms. It's just the duration is different, but they're always over these intervals of 1/3 of the symbol interval. And so you say, well, suppose I have basis vectors which go from 0 to TS over 3, and then another one that starts at TS over 3 goes to 2TS over 3, and then the last one, it starts at 2TS over 3 and goes to TS. And you think, well, they're orthogonal from one another, because if I take the inner product of any 2 of them, of course there's no overlap, so that's going to give me 0. So if this is my candidate phi1, my candidate phi2, my candidate phi3, I can see that phi1 is indeed parallel all of them. And remember, for a basis, a signal space, the inner product of 2 signals is, by definition, the integral over the symbol period of the product. So yes, these are indeed orthogonal to one another. Are they orthonormal? Well, I can normalize it to make them orthonormal, make them of unit energy. And in fact, to do that, I would want that C1 squared of t dt, I want it to equal to 1. So let's say I put an amplitude here. Then that would be the amplitude squared times, and then the interval is TS over 3. And I want that equal to 1, so that tells me that A should be equal to the square root of 3 over TS. And so I'll just put that right here. This is the square root of 3 over TS. Same height for all of them. So I have made a collection of orthonormal vectors. But do they span the space? Can all of the symbols be represented as a linear combination of these basis vectors? And I think it's quite clear that that is the case. And let's go through that exercise. So let's take symbol 1 of t. Well, in that case, it's pretty simple, because that waveform for S1 looks very much like C1. The only difference is a normalization. So I'm going to have to take C1. All of these heights, by the way, are 1. I didn't mark it down here. I guess I can do that. This is the height of 1. So S1 of t, I just have to multiply by the square root of TS over 3 times C1 of t. And, okay, so this basis collection of basis vectors allows me to find that first signal. How about the second signal? Okay, so that's going to be made up of these 2. So I need the square root of TS over 3 C1 of t plus the square root of TS over 3 C2 of t. S3 of t equals, well, it's the last 2, so it would be square root TS over 3 of C2 of t plus the square root of TS over 3 C3 of t. And finally, S4 of t Well, that would be the square root of Ts over 3 C1 of T C2 of T C3 of T. So things are looking good so far. I have been able to write all 4 of my signals as a linear combination of my basis vectors. So for sure, I have found a basis for these 4 symbols, and I can represent them in simple space. And if I were going to apply, first of all, a couple observations. It's a 3-dimensional space. Even though m equal 4. So the space is smaller dimension than the number of symbols. And what does that mean? What does that mean? Why did that happen? Was it inevitable? Yes, it was inevitable. Why is it inevitable? Because I can see that the fourth symbol, well, it's just the first symbol added to the third symbol. So clearly the fourth symbol is a linear combination of previous symbols. So that means that whatever space these are in, this falls in the same space. So it's very acceptable. So whenever we have a symbol, which is a linear combination of previous symbols, that means that the signal space will be smaller than the number of signals in the constellation. So we're getting there. We've got our vectors in signal space. Finding for the signals, but I guess I should have wrote out in signal space. Signal space. What do we need for signal space? A good normalization. Remember, normalization, very, very important. So if I were going to write the coordinates for these vectors in simple coordinates, and so I'll call these like the IQ. Of course, it's not 2-dimensional, so there's IQ and whatever the next ones are. But it would be something like, this would be 1, 0, 0. S2 would be 1, 1, 0. S3 would be 0, 1, 1. And S4 would be 1, 1, 1. Okay, so this would be, modulo normalization, so like an arbitrary normalization that I could have used. In this case, I would have to take another step in order to make it a signal space representation. A couple observations before we go on. We can see, first of all, that these 2 vectors have the same length, so they have the same energy, but it's a different energy than the first one. It's a different energy from the fourth one. So these are not equal energy. So I'll just put down not equal energy. Variations of exams from one year to the other, basically I'm asking different kind of questions. That's why I sort of answer all the questions I thought I might have asked in the exam, even though in this particular case I did not. So not equal energy, not equal length, not equal energy. And now if I want to make the correct normalization, how do I do that? Well, I have an equation, and it says to go from IQ to signal space. I use this equation, and the equation says it is the old coordinates, A, I, A, Q. In this case, we're going to have 3 coordinates, but same equation. And I have to multiply it by some scaling factor. And the scaling factor I use is m times ES divided by the square root of the squares of the coordinates. AI squared plus AQ squared. For all of them. So for, square root should be over the sum. Okay. So this is basically calculating the energies and 1 over m, getting the energies, and so this is why this works. So as I mentioned, here I just have 2 coordinates as if it was in a 2-dimensional space, but it's however many coordinates I need to make it. So let's start doing it here. So we would have the length of S1 squared would be 1. The length of S2 squared would equal 1 plus 1 equal 2. That's the same as S3. And S4 would be equal to 3. Now if I did this summation, I would get 1 plus 2 plus 2, because there's 2 of these, plus 3, and that gives me 8. So now for the normalization, I would say it was, there's 4 symbols in the constellation, ES, divided by 8. Yeah, they're all under the square root. Sorry about that. Okay, so they're all under the square root, and so this is the square root of ES over 2, and that is what I would have to multiply by each one of these coordinates. So let me be a little lazy here, and I would say that the only thing I have to do is multiply this by the square root of ES over 2, and now, multiplied by the square root of ES over 2, and then I would have the coordinates in signal space. So that would be find the basis vectors. That would be these 3 basis vectors here. And find the vectors for the signals. That would be here, and with this normalization of the square root of ES over 2 in order to get the right answer.